Hello. So, welcome to the third lecture for complex numbers and quadratic equations from class 11th mathematics. So, till the last class, we had learned about we started with algebra with respect to complex numbers. So, we had done the addition of two complex numbers, and we also saw how we can find the difference between two complex numbers. So now we will move forward with multiplication and division. So as if you consider two complex numbers, that is Z1 and Z2, and okay, so you have Z1 and Z2. So Z1 is A plus IB and Z2 is C plus IB. So when we are defining the product for two, so we want to find the Z1 and the product of Z1 and Z2. So if you expand, okay, so if you just write it in the general form, C plus ID. Okay, so if how you normally add two different, equations or two different values in brackets. So if you expand, if you uh, open up the brackets, so what you get is AC plus IB multiplied by C, and then you multiply IDA plus over here you get I square BD. Okay, so this is what you get when you open up the brackets, you expand the brackets over here. So if we keep over here, since we know that I square is actually is equals to -1. So if we write it again, B dot C plus I A D, and over here we substitute I square with -1. So you have negative. Okay, so you have negative of BD. Now what we will do is we will club the real parts to one side and we will take the imaginary parts to in the other bracket. So what we are left with is AC minus BD in brackets and plus you have I AD plus BC. Okay, so this is what we get in terms of the product of two complex numbers Z1 and Z2. So in the so if we write in the form, like whenever we want to find the product or the when we do multiplication of two complex numbers, the general form that we will write it in AC minus BD plus I AD plus BC. Okay, so this is what we have to remember when we are trying to find the product of two complex numbers. So I will show examples once we are done with the basics of the this multiplication of the complex numbers. So let us we when we were doing the addition of two complex numbers, we saw the sum of two complex numbers had to follow some properties and they had to satisfy some laws. So the similar some of the similar laws actually apply even when we are trying to do multiplication of two complex numbers. So let's see. So the first one is the closure law. Okay, so now since the product between two complex numbers is written in the form of BD plus I BD plus BC. Okay. Okay, so this is a general form. Now over here you can see that this product, if we call this as Z, the product of Z1 and Z2 is Z. So over here we can see that actually the real part of the Z is equals to AC minus BD and the imaginary part of Z is actually I AD plus BC. Okay, so in itself, since Z is can be written in the form of a real uh, component and the imaginary component of Z, it has real and imaginary component. Hence, this Z itself is a complex number. Okay, so we can see that the product of two complex numbers gives us a complex number. So hence the closure law is satisfied when we are trying to do multiplication of two complex numbers. Let's see the commutative law. So over here, let's take an example of Z1 is equals to 5 plus 2i, and we will take Z2 is equals to 8 plus 2i. So let us solve for the left hand side part first. So we will find the product for Z1 and Z2. Okay, so this is the form that we have. So let us write it in that form. So this is if write this in the terms of A, B, and C, D, and you can substitute for A, B, C, and D in this general form of the product of the two complex numbers. So what you get is 5 multiplied by 8 minus, so BD, so that is over here 2 multiplied by 2, okay, plus I outside, and then you get the product between A and D, so that is 5 multiplied by 2 and plus 2 multiplied by 8. Okay, so if you simplify it, solve further, what you are left with is 36 plus I 26. Okay, so this is Z1 into Z2. Now, if we try to solve for the right hand side of this equation of this statement, so we get Z2 multiplied by Z1. Similarly, now if you the general form, you can substitute the same components because they don't really change much. So over here again, you put 8 into 5 minus 2 into 2 plus I. So you have AD. So 2 into 5 plus BC. BC, so that is 8 into 2. Okay. And you are left with if you solve the bracketed portions and you simplify it, you are going to get 36 plus I 26. So that is equal to what we were getting when we were multiplying Z1 with Z2. Therefore, Z1, Z2 is equals to Z2, Z1. Okay, so this remains the same. Now we will see if the associative law also holds good for the multiplication of when we are trying to find when we have three complex numbers. So let us take Z1 is equals to 5 plus 2i, Z2 is equals to 8 plus 2i, Z3 is equals to 5 plus 3i. Okay, so let's solve with respect to this. So the left hand side of the statement, we have Z1, Z2, Z3. Okay, so first we will solve for Z1 into Z2. Okay, so we will get this as 5 plus 2i multiplied by 8 plus 2i. Okay, and the entire product is then multiplied by 5 plus 3i. Okay, so now this we already saw in the previous example. So that was actually 36 plus I 26. Okay, or you can, okay, So 26i, then 5 plus 3i. Okay, so you repeat and you get, you consider this as a plus bi and this as c plus di, then put it in the same, the general form of a product of two complex numbers. 36 multiplied by 5. Okay, so that is AC minus, you have BD. Okay, so 26 multiplied by 3, and then addition I, and then what is the other part? That is the AD plus BC. Okay, so AD is 36 multiplied by 3 plus BC. Okay, so 26 multiplied by 5. So you get this as, okay, so you solve it further. What we are getting is 102 plus 238i. Okay, so this is what we get for Z1 or Z2 and the product of Z1, Z2 multiplied by Z3. Now, if we consider the right hand side of the equation, so we have Z1, Z2, Z3 is equals to, okay, so now we write the complex numbers. Z2 is 8 plus 2i, okay, multiplied by 5 plus 3i. So first we will solve for Z2 into Z3. Okay, so we keep 5 plus 2i. Then again, considering this as A, B, and this as C, D, we write it in the general form. Okay, so that you have AC, so AC, A into C, so that is 8 into 5 minus 2 into 3. Okay, and plus, keeping I outside, we have AD plus BC. Okay, so AD plus BC. So 8 into 3, 8 AD plus BC. Okay, so that is 5 into 2. Then you simplify the square brackets first. So you get 40 minus 6 plus I 24 plus 10. Okay. What you are left with is 34. 34 plus 4. I. If you solve this now, so again you take it in the similar form. So I will just write it here, so you can refer to this when you are practicing. So AC minus BD plus IAD plus BC. Okay, so you have AC already done, then minus BD, so that is 34 multiplied by 2. Okay, so the minus sign comes because we get I square when we multiply the BD actually. Then you have plus I, so that is again AD plus BC, sorry. So A and D, so that is 34 multiplied by 5, okay, plus BC. So this is BC, so 34 multiplied by 2. Okay, so I will just write the final answer over here. Okay, so again you get 102 plus 238i. Okay, so you can see that the left hand side is equals to the right hand side. So this is how we know that the associative law is also valid when we are considering the multiplication of two complex numbers. Okay, so now we move on to the another property, which is actually implying that there exists a multiplicative identity. Okay, so there is a term called multiplicative identity. So that means if we have a complex number, okay, which is say 1. Okay, so if you have a complex number which is equals to 1, so you can write it in terms of the complex number as is equals to 1 plus 0 I. Okay, so this is actually the multiplicative identity. Identity. And if you multiply any complex number with this with multiplicative identity, you will get the same complex number. So if you have z1 is equals to 5 plus 2I, and so you multiply it with a multiplicative identity. Okay, so if you have z2 is equals to 1 plus 0I. So if you multiply these two together, so if you write it in the same form, okay, so z1 or z2, okay, is equals to you have AC minus BD plus I AD plus BC. Okay, so over here AC is 5 and this will be 0. Okay, and then plus I, you have AD. Okay, so this is 0 again, and you have plus BC. So this is again 2. Okay, since I is kept outside, and what you are left with is 5 plus 2I. Okay, so then this is equals to your Z1. Therefore, so Z1 multiplied by the term or the multiplicative identity that you can also write as 1 or 1 plus 0I is going to be equal to the complex number itself. Okay. So now we come to another property, which is the which talks about the existence of multiplicative inverse. Okay, so when you have a complex number as z is equals to a plus ib or a plus bi, in whichever form you write, there is a multiplicative inverse that exists for z, which can be written in terms of a plus a square plus b square plus I a minus b or a square plus b square. Okay, so this is what we get. Suppose we try to find out, okay, that how are we getting this expression. Okay, so suppose we consider z is equals to a plus bi. Okay, so if we take it as 1 by z, okay, so you have 1 by, sorry, okay, so a plus bi. Okay, so if you want to write it in general terms or you want to solve this further, okay, so this is what we normally we can see, but this is written in terms of z inverse, the multiplicative inverse. Okay, just wait a minute. So this when you write in terms of a plus a square plus b square plus I minus b upon a square plus b square. Okay, so what you are getting it is a minus bi upon a square plus b square. So whenever you want to write the multiplicative inverse of a complex number, you can directly write it in this form itself. Okay, so if you have considering z1 is equals to 5 plus 3i, and you have to find the what is what is the in multiplicative inverse of Z. Okay, so you can write it in terms of Z1. Okay, so that is equals to your A, so that is 5, 5 upon 5 square plus 3 square, okay, plus I. Now you get the negative sign of 3 and again divided by the same denominator. Okay, so what you're left with is minus 3i. Okay, so 5, 3i. Okay, so we take 25 plus 9, so what we get is 34. Okay, so this is actually what we get as the inverse or multiplicative inverse of Z1. Okay, so when we are trying to solve any problem in the sense of where we have been asked to find the multiplicative inverse, so you write this and you solve this this general form. Okay, so you can come to the normal form of complex number. So if you want to, justify, you want to write it in the form of complex number itself, you can write this as 34 minus 34 I. Okay, it is also Z1 inverse. Now let's see the another law, that is the distributive law. Okay, so if you have three complex numbers, so we will take again the similar examples as we had taken before. 5 plus 2i, z2 is equal to 8 plus 2i, then z3 we are taking as 5 plus 3i. Okay, so we will first solve for the a, the statement of a, z1, 2 plus z3. Okay, so first let's see, we'll try to solve for the left hand side of the equation. We will see if this can be validated. Okay, so first we will do the addition of Z2 and Z3. Okay, so let's keep Z1 as it is. Z2 is 8 plus 2i plus 5 plus 3i. Okay, so that is equals to Z1. So you add the real parts and the imaginary parts. So 8 plus 5, so you have 13 plus 5i. Okay. And then you substitute for your Z1. So that is 5 plus 2i and 13 plus 5i. Okay. So let's solve. Again, if like we have to remember that the product of two complex numbers can be written in the form of AC minus BD, okay, plus AD plus BC. Okay, so in the similar form, if you write it over here, so what you are left with is AC 13 multiplied by 5, okay, minus BD, so that is 5 into 2 plus I AD 5 into 5 plus BC 13 into 2. So what you get is 65 minus 10 plus I 25 plus 26. So what you are left with is 55 plus 47i. Okay, so this is actually Z1, Z2 plus Z3. Okay, so and now we try to see if with this simplified, version, simplified the form of Z1 and in bracket Z2 plus Z3, it actually gives the same results or not. So we can see if it is validated. Okay, so now the right hand side. So this was the left hand side. Now we do the right hand side. So Z3. So we write it in the, we substitute the numbers, complex numbers. So 5 plus 2i and 5 plus 3i. Okay, so we solve for these two. We have to find the product. We have already seen for this this multiplication or this product between the product of these two numbers. So that comes out to be 36 plus I 26i. Okay, let's solve this. We get AC minus BD, so that is 6 plus I AD, that is 15, multiply plus BC, that is 10. So what we get is 36 plus 26i plus 19 plus 25i. Okay, then you try to add them. How we normally add two complex numbers. So the real parts and the imaginary parts are added. So what we get is 19 plus 36. We get 55. Okay. So I'll just write it on the left side for each. Okay. So what we are left with is 55 plus. There's a difference. Sorry, there's yeah, this was wrong. This was wrongly solved by me. This corrected. Okay. So where 20 plus 25 plus 26 is actually 3i. Okay. So I'm extremely sorry for that mistake. So you get the similar. Okay. So when you add 26 I plus 25i, so you get your 53i. Okay. So you can see that the results match, and hence we can say that this property is also validated when it comes to the distributive law. Okay, Z1 multiplied by Z3. Okay, so this is validated. Now let's see if if you try to see in the associative law when applied to this distributive law is also valid or not. So we will see it in the okay. So the next statement that we want to see, or the next property that we want to see if it is valid or not, is Z1 plus Z2 Z3 is equals to Z1 Z3 plus Z2 Z3. Okay. So if you solve, we are taking Z1 as 5 plus 2i. Okay. Plus the Z2 we had taken as 8 plus 2i. The whole thing multiplied by 5 plus 3i. Okay, so let's solve for the LHS part. So there we first solve the addition part of this. We'll see if it is working, if it is valid. So let's first add these two complex numbers. So what we get is 8 plus 5 to have 13 plus 4i. Okay, and multiply it by 5 plus 3i. So what we get is, again, we try to put it in the form of multiplication of two complex numbers. So you have 13 multiplied by 5. So that is AC minus BD. So 4 into 3 plus I. You have AD 13 multiplied by 3 plus BC. Okay, so that is 4 into 5. So what you get is 65 minus 12 plus I 26 plus 20. Okay, so then you get this as 53 plus 46 I. Okay, so this is the LHS part. Let's do the RHS. So that is the simplified version of Z1 plus Z2, the whole brackets multiplied by 3. So you have Z1 multiplied by Z3. So that is 5 2I. Okay. Then Z3 is 5 plus 3I plus Z2 is 8 plus 2I multiplied by 5 plus 3I. Okay. So we solve these two, this product, and we find the product of these two complex numbers also. So again, A, C, B, D, A, B, C, D. Okay, so we get AC, so that is 25, minus BD, so that is minus 6, plus I, the AD, okay, so that is 15, plus BC, plus 10. Okay, so this is Z1 into Z3, then you add it up with the product of Z2 and Z3. So again, we write this in the form of the general multiplication form. So AC 40, okay, minus VD. So you have minus 6. Then you have plus IAD. So that is 24 plus BC. So 10. Okay. So you solve the brackets, you simplify it. What what we are left with is 18 plus 25I plus 34 plus 34I. Okay, and then you again simplify these two brackets, you add them up. So what we get is 18 plus 34 plus I 25 plus 34. I think I have done some. What is this? No, sorry. I again made a small mistake. Okay, so this is 49. Okay, so again we see 18 plus 34 is again 53, and what we get is 49 I. Okay, so this is the RHS. So as we can see that LHS is equals to RHS, then this identity or this property is also validated. Okay, so we can see that multiplication of two complex numbers actually, they satisfy a number of properties like the closure law, commutative law, associative law, and the distributive law. And when we are trying to, there are two terms or two mathematical terms that are existing because of the multiplication algebraic form of complex numbers. We have multiplicative identity as well as a multiplicative inverse. Okay, so we saw how these are how these properties have to be satisfied when we are trying to do the multiplication of two complex numbers. Okay, so if we want to see an example of the multiplication, okay, so let's see if we can do. Okay, so suppose you are given, you have to prove that the real part of Z1, Z2 is equals to real part of Z1 multiplied by real part of Z2 minus imaginary part of Z1 multiplied by imaginary part of Z2. Okay, so you have to prove this. So if you have to prove this, now consider Z1 is equals to A plus IB and Z2 is equals to C plus ID. Okay, so this is what we get. Now, if you remember, okay, so the product of Z1 dot Z2 is equals to AC minus BD plus AD plus BCI. Okay, this is something that we know. Now, let's take the real part of Z1, real part of the product. Okay, Z1, Z2. So this is actually the real part and this is the imaginary part. So real part of Z1, Z2 is equals to AC minus BD. Okay, now let's see if the product of the real part of Z1 and real part of Z2 and minus imaginary part of Z1 and imaginary part of Z2, what is the value that we get for that. Okay, so the real part of Z1, not real part of Z2, what we get is A multiplied by C. Okay, so this is the real part of Z1 and C is the real part of Z2. Okay, now if we get the imaginary part of Z2 and the imaginary part Z1 and imaginary part of Z2. Okay, so if we are only considering the coefficients of it. Okay, so this is the imaginary coefficient of Z1 and D is the imaginary coefficient of Z2. Okay, so you multiply them. So what the right hand side then comes up to LHS part. Okay, therefore LHS equals to RHS, hence proved. Okay, so this is an easy way to also know that kind of denote that the real part of the product of two complex numbers is going to be the difference of the real coefficients of the individual complex numbers and the imaginary coefficients of the uh, uh, of your complex numbers. Okay, so this is what we can understand from this. Actually, this is also going to have I. Okay, and this becomes BD I square. Now, since we know that I square is equals to minus 1, I had actually skipped this step entirely. So that is actually minus BD. Okay, so the RHS then becomes AC minus BD. Okay, if we try to get in terms of this. So now we will move on to the division of two complex numbers. Okay, so over here we find the use of multiplicative inverse that we had defined in the previous portion. Okay, so suppose we are trying to find like we have two complex numbers and we want to find what we get when we divide the two numbers. Okay, so sometimes we have to use the division operator to get um, uh, we have to operate between two complex numbers. Okay, so what is actually if you have Z1 and Z2, okay, so we can write this as Z1 multiplied by 1 upon Z2. Now remember that 1 upon Z2 then actually becomes Z2 inverse, so which is the multiplicative inverse. Okay, inverse of Z2. So why do we do this is because then it becomes easy Okay, is for us to simplify and solve when we want to divide a complex number with another complex number. Okay, so let's see with an example. Okay, so yes. Okay. So for division, let's say Z1 is equals to 5 plus 2i, Z3 is equals to 8 plus 2i. Okay, so uh, we have these two numbers, so we have to find, sorry, this should be Z2. Z2. Okay, so we have to find Z1 by Z2. So you can write this in terms of Z1 multiplied by 1 by Z2. Okay, so this, if you write it 1 plus 2i multiplied by 1 upon 8 plus 2i. Okay, so if you remember the form of Z1 that we get, okay, if you have Z is equals to a plus bi, so that is a square, a upon a square plus b square plus I negative of b upon a square plus b square. Okay, so if you write this term in terms of the multiplicative inverse by 2i, okay, so 8 upon 8 square plus 2 square plus I minus 2 on 8 square plus 2 square. Okay, so you solve the right side bracket, 8 minus 2i. So this is 64 plus 4. Okay, so you get 68. Now you do the multiplication between these two. Okay, so it was easy to convert the division into a multiplication. Okay, so now we can use the similar form as we had found. The product of two numbers can be written in the form AC minus BD plus IAD plus BC. Okay, so in this form, we can then write this as, let's take out 1 by 68, okay, to ease out the process further. So you have 8 AC minus BD. Okay. So this actually, if you write this in terms of minus, so you have plus minus 2. Okay, so this is your D actually. So what we get is, when we try to find for BD, okay, so one negative sign already comes because of the I square that is present, and this becomes minus 4. Okay, and then you have, so this is AC minus BD plus I we get AD. Okay, so that is again minus 10 plus BC, so that is 16 by 68. So what we are left with is 44 plus 6i. Okay, and if you divide the so if you want to simplify it further and you want to take it out, so if you divide the thing, divide all across by 2, if you write this in terms of 44 by 68 plus 6 by 68, and you divide the terms with 2, what you are left with is 2 by 34 plus 3 by 34 pi. Okay, and further simplified, 22 plus 3 pi. Okay, so this is what we get when you want to divide two numbers. Okay, so let's see some a bit more complicated examples of say multiplication. Okay, so suppose you are given if 1 plus I, 1 plus 2I, 1 plus 3I, 1 plus Ni is equals to A plus IB. Okay, then what is 2 multiplied by 5 multiplied by 10, 1 plus n square? What is the value? Okay, is the value for, okay, so we have to get the value of this. Okay, so now we already have 1 plus I, 1 plus 2I, 1 plus 3I plus 10I is equals to A plus IB. Okay, so suppose we change these signs all across. Okay, so this is your 1. We change the sign on both these sides of the equal to sign. So what we get is 1 minus I, 1 minus 2I, 1 minus 3I, dot, 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 1 minus Ni. Okay, so that will be equals to 1 minus IB. Okay, and this we consider as our second equation. If we now multiply, okay, multiplying 1 and 2. Okay, so if we multiply each of the terms of 1 and 2, so what we get is, okay, in easier terms, if we just write it, 1 minus I, okay, then you have 1 plus 2I, 1 minus 2I, 1 plus 3I, 1 minus 3I, okay, dot, 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 1 plus Ni, 1 minus Ni, okay, is equals to A plus AB and A minus IB. Okay, so if you take these brackets together, what you get is 1. If you the general form of the identity, okay, A plus B multiplied by A minus B is equals to A square plus, sorry, not plus, it's, so that is A square minus B square. Okay, so in the similar form, we can take the common, the brackets which fall into this form and write them in terms of this. Okay, so this is 1 minus I square, 1 plus, sorry, this will be, so this will be 1 minus 4I square. Okay, then you have 1 minus 9I square. Okay, dot, 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 dot. 1 minus Ni square. Okay, and this will be A square minus Bi or Ib, whatever, in whichever terms you write. Okay, so now we substitute, since I square is equals to minus 1. Okay, so that means all the signs are going to change now for the numbers that are there. Okay, so this becomes 1 plus 1, 1 plus 4, 1 plus 9. This becomes 1 plus n square is equals to b square plus b square. Okay, now you can write this in terms of the form that is asked in the question itself. So you can see 2 multiplied by 5 multiplied by 10 multiplied by 1 plus n square is equals to a square plus b square. So this is the answer. Okay, so this is how we can see how the multiplication of complex numbers can be used. Now let's try another algebraic. We had done addition and subtraction before. Let's now try to find the values of few variables using such algebraic operations. Okay, so the question is, what are the values of x and y if 1 minus I x plus 1 plus I y is equals to 1 minus 3I. Okay, suppose this is your question. Now we simplify the LHS part. Okay, so what we get with 1 minus ix plus 1 plus I y. Okay, so this we can write it in terms of x plus xi y plus yi. Okay, then you separate out the real parts. X plus y plus, okay, so sorry, this will be minus over here, minus. Okay, then you can have y minus x I. Okay, now we know that this is actually equal to 1 minus 3i. Okay, now so we equate the real parts and the imaginary parts. So therefore we get x plus y is equals to 1. Okay, and y minus x is equals to 3. Okay, now we will try to substitute, and probably we'll first start with substituting for y. So y is equals to 3 plus x. Okay, sorry, this is minus 3. Okay, so minus 3 plus x. So now we substitute for y in this equation. Okay, so x plus, in the place of y, we write x minus 3 is equals to 1. Okay, so that will give us 2x is equals to 4. Okay, so therefore x is equals to 2. So we found the value of 2. Now we substitute the value of x in this equation, okay, to get the value of y. So now y is equals to minus 3 plus 2, and that is minus 1. Okay, so therefore x comma y is actually equals to 2 comma minus 1. Okay, so now we found the solution for x and y. So over here mostly the operator that was mainly used is the addition. Okay, now let's see if we can do the similar. We try to find x and y when we are using another operation. So the question is, if x plus iy and 2 minus 3i is equals to 4 plus I, what are x and y? Okay, so let's first simplify the left hand side of the statement that we have. So that is x I y 2 minus 3 I. Okay, so again AC minus BD plus I AD plus BC. Okay, so we write it in terms of that. So AC is 2x and BD is minus, you have BD, so that is minus 3. Okay, minus 3y. Okay, minus 3y. And then you have plus I. You have AD, so that is minus 3x and plus BC, so that is 2y. Okay, So you can write this. We try to get the real parts, and then 2x plus 3y in simplified form. Okay, plus you have 2y minus 3x I. Okay, now we equate this with the right hand side of the statement that is given. So therefore 2x plus 3y plus 2y minus 3x I is equals to 4 plus I. Okay, therefore we have 2x plus 3y is equals to 4 and 2y minus 3x is equals to 1. Okay, now again we do the similar thing. We try to substitute for either x or y, and then we resubstitute it into the other equation. So let us first try to see if we can simplify. Okay, so if you have 2x equals to 4 minus 3y, okay, so that x is equals to 2 minus 3 by 2y. Okay, so let's substitute this in this equation. Okay, so maybe we can write this as equation A and this as equation B. Okay, so and this is C. So substituting C into D, sorry, C into the equation B, we get 2y minus 3. Okay, 2 minus 3 by 2y equals to 1. So we solve this. 2y is equals to 2y minus 6 plus 9 by 2y is equals to 1. So 2y is equals to 1 plus 6 minus 9 by 2y. Okay, so 7 minus 9 by 2y. So that actually comes down to, if you get the y products on one side, okay, so what you are actually left with is y is equals to 14 by 13. Okay, now you substitute for the y value, say in equation C. So what we get is, okay, so x is equals to 2 minus 3 by 2 multiplied by 14 by 13. Okay, so that is equals to 2 minus 21 by 13. Okay, so you actually divide this, cancel it out, and what you get is 5 by 13. Okay, so therefore the answer, I'll just write it here, is that x is equals to 5 by 13 and y is equals to 14 by 13. Okay, so this is how we can find values of variables when we are trying to get the algebraic operators of complex numbers into play. Okay, so for today we will be ending here, and in the next class we will go further with some more examples of where we use the addition, difference, multiplication, and division of complex numbers, and also we will move forward with the next section of complex numbers. So, thank you so much.